going to prove a corollary to Bezout's lemma. It says that if a and b are integers not both 0, then the set of all linear combinations of our a and b is precisely the set of all multiples of the GCD of AB. That is, any linear combination of a and b is a multiple of the GCD. Heavy statement. It's an if and only if, because it's precisely this set. This here is precisely the set of all multiples. So it's an if and only if proof. Here we're given that T is the set of AX plus BY such that X and Y are integers. And I want to show that these are all multiples of D. Well, D is equaling to the GCD of A and B. I prefer not to use X and Y's here. How about we say AU plus BY? How about BV? For U and V in Z. Okay. Now the GCD is some multiple linear combination of X and Y. Well, this is in T. Okay, now I need to show that everything in T is a multiple of D. Okay, so we let A X prime plus BY prime be in T. Okay. Now I need to show that it's a multiple of D. Okay, so let's say that. Is AX prime plus BY prime a multiple of D? Well, it is if D divides that. Okay. Yes, if D divides AX prime plus BY prime. But remember, D is the smallest linearcation. Sorry, the smallest linear combination. But this is true as D is the smallest element of T. Now here, these can be negative, but let's not worry about that. D is the smallest element of T. So D does divide AX prime plus BY prime. You know, we can say it divides that, okay? But that implies that the absolute value of this linear combination is a multiple of D. But that implies, I don't care if this is positive or negative, that means that this is a multiple of D. It might, these M and N don't need to be the same. Like, if this N is -7, well then this N is +7. But that's what I wanted to show. That any element in T. I picked an arbitrary element in T, and I showed that it's a multiple of D. That's all I wanted to show. Now we do it the other way. We assume the set of all multiples of D. Let T prime equal the set of all multiples of D. I want to show that that T prime equals T. I want to show that T prime equals T. Okay, so let, I don't know, E be an element of T prime, which implies E is some multiple of D. Now I want to show that E is in T. So this is Q times AX plus BY, because that's D. Well, this is A times QX plus B times QY, but by definition, that's in T. It's a linear combination of A and B. And that finishes that proof. Okay, let's move on to the next theorem. It says that A and B are integers not both 0. Then A and B are said to be relatively prime. That is, the only numbers that go into both of them is 1. If and only if there exist x and y in Z such that there's a linear combination of A and B that equals 1. AX plus BY equals 1. Proof. So what we have here is A and B are relatively prime. But that implies that the GCD of A and B is 1. That's the definition of relatively prime. I can even say if and only if. But if the GCD of A and B is any number, then that number, in this case 1, is a linear combination of A and B. But that's what I wanted to show. There exist x and y. Let me state that. For some x and y in the integers. Now we go the other way. We assume that 1 is equal to, for some x and y, 1 is equal to ax plus by. I'll even say that. For some x and y, let's say assume for some x and y that 1 is equal to ax plus by. Now, the GCD is always in the form of ax plus by. And it's always a positive number, positive integer. There's no way out except for the GCD of A and B to be 1. Okay, that implies that the GCD of A and B is 1. Can't be any smaller. Can't be any smaller. Okay, but this implies by definition, I can even say if and only if, that A and B are relatively prime. That finishes that theorem, the proof of that theorem. The next one is the corollary of that previous theorem. It says if the GCD of A and B is D, then the GCD of A over D and B over D is 1. Well, let's prove this. First thing I want to argue is that A over D and B over D are integers. Okay? The GCD of A and B equaling D implies that D divides A and D divides B. Well, that implies that A over D and B over D are integers. And after all, what does it mean for D to go into A evenly? It means it's an integer. This means that D goes into A. A is a multiple of D, so dividing both sides by D, you get that C over A over D is M. A over D is an integer, B over D is an integer. Okay, so now we can talk about the GCD of those two numbers because those numbers are integers. Now, since the GCD of A and B is D, that means D is equal to AX plus BY for some pair of integers, X and Y. Now, we divide, let's do this on another line. We divide both sides by D. So 1 I can write as A over D times X, and A over D is an integer, plus B over Y times Y. And B over Y is an integer. But by the previous theorem, if an integer multiple of X and an integer multiple of Y is 1, that implies that the GCD of A over D, I'll change that, and B over D is 1. A over D. It implies that. That completes that corollary. The next one is nice. So let me write proof. It says that if A divides B and B divides C and the GCD of A and B is 1, then AB divides C. Well, let's just go by definition. A divides C implies C is a multiple of A. Got that one. B divides C implies that C is probably, or not necessarily, but a different multiple of A. We got that. This tells us that there exists X and Y in the integers such that AX plus BY is 1. Now, what I want to show is that C is some multiple of AB. That's what I want to show. So I'm motivated to multiply by C on both sides, because on the right side I get C. Multiplying the left side I get CAX plus CBY. I want to factor out an AB. And you're like, shucks, over here I only have A, and over here I only have B. But I can write C using A, and let me fix my typo here. B divides C means that C is a multiple of B. And I can write C using B's. So here I have my AX, but I want C to have B in it. Ooh, C is NB. So now I'll be able to factor out AB. Plus, over here, I have BY. I have a B. I want C to introduce an A. Oh, C equals MA. This is looking really good. So I can factor out AB. So I have AB times NX plus MY is equal to C. Well, you know what? That implies that that implies that AB divides C. That implies that AB divides C. And that's exactly what I wanted to show. I wanted to show that AB divides C. That is, C is a multiple of B. C is a multiple of AB. That is, C is some multiple of AB. Once I have that, that implies this. In fact, it's if and only if AB divides C. As always, if you like videos like this, definitely subscribe to my channel, leave a comment, like my channel please. See you folks in the next video. Most of all, watch and learn.